So I have a very special guest with me today. Her name is Julia, and she's going to teach us all about exoplanets. Hi, Julia.
Hey, Kathy. Hey, everyone. Nice to be here.
So, Julia, where are you right now?
Right now, I'm in Oakland, California with my cat named Bella.
Well, hello, Bella. And Julia, what do you do?
I'm an astrobiologist, which means I study life in the universe. So my day job is working for a program called SETI, which stands for the Search for Extraterrestrial Intelligence. So I literally look for aliens.
That is so cool. And what are you going to teach us today?
Today is going to be all about exoplanets. And an exoplanet is a planet that orbits another star other than our own.
Well, that sounds amazing. I can't wait to learn more.
Let's go ahead and get started. I want to know what you know about exoplanets. So I want you to take a few seconds, a few moments to think about, have you even heard that word before? What is an exoplanet? So an exoplanet is a planet that goes around another star. But before we get into exoplanets, we are going to do a recap. There are about 400 billion galaxies in the universe, and each galaxy has about 400 billion stars.
And all these galaxies are in the universe. What's the universe?
The universe contains all of space and time that we can detect. So it contains everything. And if we zoom in to the universe, we see that there are galaxies. When we look into outer space with our big telescopes, all those little blobs that have letters and numbers next to them are galaxies. So there's a lot of galaxies out there. So all of these blobs that you're seeing kind of flying at the screen are galaxies. And I mentioned about 400 billion galaxies in the universe, and each one of those galaxies contains on average about 400 billion stars. And in our galaxy, this is not really our galaxy, but this is a galaxy. But if we were to pretend this was our galaxy, we live about 2/3 away from the center. That's where our star and our solar system is.
But there's lots of different kinds of stars, right?
There are stars of many different colors. When you go outside and on a very clear night, you can see stars that are red, maybe even a little blue colored, white and orange. Colors like blue and white are actually hotter stars than ones that are yellow and orange and red.
And it's not just that there's different colors of stars, but there's also different sizes of stars too.
These are big stars over to the right and little dwarf stars on the left. And our star is actually a really small star. We call it a yellow dwarf, and it's not a super hot big star, but it's kind of a smaller, cooler star.
And we know our solar system has planets going around our star, and maybe other solar systems have planets too. Why is it important to know about these planets?
So we want to know, kind of the biggest question, at least in my opinion, is are we alone in the universe? Is there other life forms out there, perhaps on another planet in our solar system, like on Mars, or even around a star that might have planets around that star? So when you look up at the night sky, I want you to wonder, are we alone? Are there other planets around those stars out there? We call planets that go around another star an exoplanet, and we're going to talk about how we detect exoplanets. So how do we detect them? By looking really, really carefully. NASA is detecting exoplanets. This is an outdated slide, but we have a few ways that we've detected exoplanets, and NASA is keeping track of them. So right now, this slide says we've confirmed 4,025 exoplanets as of July 25th, 2019. But today, as of today, we've actually confirmed 4,144 exoplanets. So in the last 20 years or so, we have discovered 4,144 exoplanets, which is amazing. It's an amazing time to get into astronomy, to be curious about life out there, because we are doing the right things to try and find exoplanets around other stars.
So how do we find exoplanets?
There are three main methods that I'm going to be talking about today. One, the wobble method, two, the transit method, and three, direct imaging. There are other ways we can detect exoplanets, but I'm not going to talk about them today. So the first way that I'm going to talk about detecting exoplanets is called the transit method. So that's when a planet goes in front of the star and it dims the light of that star just a tiny, tiny little bit. So I'm going to explain how this happens. So this is a picture of our star, our sun, and you can see that there is a planet going in front of this. This is what we call the transit of Venus. So we're on Earth looking at our star, and we see that there's a planet going in between the Earth and the sun. If you think about this image of our star, this was taken through a telescope, you can imagine, you can break down this star, this picture of the star, you can think of them as pixels. I don't know if you've heard the term pixels, but you can think of like if you were to draw kind of like a grid over the star, and how many kind of squares would this planet take out from the overall light coming from the star. So it wouldn't take away too many pixels, but it would dim the star just a tiny, tiny, tiny bit when you look at the overall output of the star. So this is what we call a transit, and this is a transit of Venus, and this happened in 2012. So here's another way to think about this. When we're looking at the light coming from a star, if there's a small planet that goes in front of it, it will make a tiny dip of the light. But if you have a bigger planet, like say a Jupiter-sized planet, that dip would be much bigger. So the brightness of the star would get a little bit lower if it's a small planet, and the dip would go a little bit bigger with a larger planet. So that means larger planets are much easier to detect. Okay, so here's the bright light of a star. I'm going to put this sheet in front of it, and I'm going to show you how the light dims. So I'm going to hold a little planet that's going to go in front of the star, and I want you to see, tell me what you see, if you can see the shadow. Did you all see that? All right, so that's a small planet going in front of its star. So we're going to do another one. This is a bigger planet. So I want you to tell me, what was the difference between those two shadows that you saw? Which one took away more light? I can do it again while you're thinking. Okay, so here's the small planet going in front of the star, and the bigger one. Yeah, so the bigger one definitely took away more light. So they're easier to detect. So I'm going to go back to this little planet here, and I'm going to do two things. The first one, I'm going to transit that planet close to the star and then far away. And I want you to tell me what difference you notice in the shadow. Okay. Okay, so the first one I'm going to do close to the star. So that was the small planet really close to the star. Now I'm going to do the same thing, but farther away from the star. So which took out more light? The first one, yeah. So when I had the planet going in front of my star, here comes my cat. My cat is transiting the screen right now. Thank you, kitty. When I had the small planet really close to the star, it dimmed more of the light versus when it was pretty far away. So that means that it's much easier to detect planets that are closer to their star and that are larger. So those are the two ways that we can detect exoplanets more easily. But right now we're trying to have better technology to detect small planets a little bit farther away from the star maybe at the distance say that Earth is going around our star. So that was the first method. We just learned all about the transit method, how planets go in front of the star and it dims the light of that star, and we can detect if there is a planet around that star. The next method is what we call the wobble method, or in scientific terms, we call this the radial velocity method or the Doppler shift method. There's a few names for it, but I'm going to call it the wobble method because that sounds more fun. So the wobble method is all about looking at the star and how it wobbles when a planet is going around it. So believe it or not, even though a star is so big, a little planet will still have a tug on that star, making it wobble. So that the influence of the bigger star is way stronger, pulling way more on the tug of war on that little planet than the planet is pulling on the star. But the planet still pulls on the star just a little bit, and they actually orbit each other in this center point right here. So that's this kind of, if you think of like a seesaw, that's kind of the teeter. So if you have a bigger star and a smaller planet, the star won't wobble as much. But we're going to see a few types of examples of the wobble method. So the more it wobbles, the easier it is for us to see. So by the end of this, I want you to start thinking of what type of planet and star would be the most easy to detect. Okay, so you might have heard something called the Doppler shift. I mentioned we sometimes call this the Doppler method. So we're gonna start talking about what a Doppler shift is. You've probably all heard this, but if you've ever heard like a car or an ambulance go by, you might notice that it changes the pitch of the sound. And go ahead, take a listen. Did you all hear that car change pitch? You probably heard it like a train going by or an ambulance. That's what we call the Doppler shift, when that sound changes as something is going by you. And we're going to break down the science of how that happens. So here's our car driving normally, and it's emitting sound waves. Say it's honking really loud. And those sound waves are traveling out and out and out, kind of just evenly. But say we start moving in our car. As the car is moving forward, those sound waves are going to get crunched in the front and elongated in the back. So they're going to get all crunched and squished here, and the sound waves are going to get long over here. And when we hear that crunch sound, the pitch goes a little bit higher. So we hear it higher notes, and then as the car passes us, we hear those lower notes here. We call that a change in pitch. So higher pitch here, lower pitch as it goes by. When we translate this into talking about exoplanets, we're not talking about the sound that a star makes, but the light that it emits. So when we look at light in the rainbow, we call the light coming at us, when it's all crunched, blue shifted, and when it's leaving us, red shifted. And if that doesn't really make sense to you, that's okay. You can think of it as the higher pitch sound when a star is wobbling towards the Earth, and when it's wobbling away from the Earth, that lower pitch sound. Okay? So we're looking for that change in light, but because we can't hear stars, we're trying to see if we can detect this Doppler shift through a change in its light. And this picture here is a little bit confusing, but I just wanted to let everybody know that our star wobbles, mostly due to the influence of Jupiter going around the sun. But our star wobbles, and remember, I think I was mentioning the teeter point, the seesaw. We call that the barycenter. So if you look at all these numbers, these are years, our star wobbles pretty significantly. So it's wobbled all these years thanks to mostly Jupiter and the other planets. So if there's an alien looking at our star, they could see that our star is wobbling, and that must mean it has planets, because planets that are really big will make that star wobble a lot. And if planets are really small, it will make it wobble a little bit. So we can tell a lot about how big planets are thanks to the wobble method. So here are a few more examples. Here's a big star and a little planet. Now here's a little star and a really big planet. You can see that the barycenter is not even in the star, it's beyond the star. So we know Jupiter is actually the biggest planet in our solar system, and it gives a very big wobble to our star. Okay, so I was mentioning we can't do sound in space. We can't listen to sounds. We can't listen to the star's Doppler shift sound, but we can look at its light. So remember I was talking about redshift and blue shift? This is kind of what it would look like to astronomers when they are looking through their instruments trying to detect the wobble of this star. So you can see the rainbow kind of shifting, going red shifting when the star is moving away and from us, and blue shifted when the star is coming towards us. Before the next method, I'm going to stop sharing. I'm going to see if I can do this demonstration. I have what we call a Doppler shift ball. I made it a few years ago, and I have a little sound buzzer inside, and I have to connect the circuit to make it work. And I'm hoping that you can hear when I wobble the star, I hope you can hear the change in pitch, or the blue shift and the red shift. So let's see if this works. Okay, so I've connected the circuit. Can you all hear that annoying sound? All right, so I'm going to wobble it. Let me know if you can hear the change in pitch. All right, did that work?
Yeah, that's great.
Cool. All right, so that little woo, 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 you were hearing the Doppler shift. Awesome, cool. So next time you hear a car going by, or a police siren or ambulance, listen for that Doppler shift. And then you can say, hey, this is also one way we detect exoplanets, and you will be the coolest kid on the block. Okay, great. I'm going to keep sharing my screen, and we're going to talk about the last way we detect exoplanets that I'm going to be talking about today. So we're just talking about the Doppler shift, or the wobble method. So now we're going to talk about directly imaging these exoplanets, because it would be so cool to actually see an exoplanet, or planet around another star, but it's really, really hard to do that. So there's a few ways we can do this. We can use telescopes that are on Earth, but we have to use really fancy tricks to be able to see exoplanets around other stars. Remember, stars are super bright and planets are super small, and they don't emit their own light. So I'm going to go back to my headlamp. Okay, so you can see my bright headlamp. I'm going to hold up a tiny planet next to the headlamp. It's hard to see, right?
Yeah, I can't see it.
But if we were to block out the light of this headlamp, you can see the planet a little bit better. So, hard to see, much easier to see, right? Hard to see the little exoplanet?
Right.
Much easier. So, that's how we're trying to do this direct imaging of these little exoplanets. It's hard to do. So I'm going to share my screen and show you how we do this. So there's a few ways we can do this. We have to use very fancy optical tricks to be able to image exoplanets. So what we're looking at here is probably one of my most favorite pictures ever, or I guess movies. All right, so here is the star in the center. We're blocking it out here. and we're watching these exoplanets going around the star, which is fantastic. Like, we're seeing planets around another star with our eyes. But you have to use a lot of fancy optical tricks to do it, and it's very hard. And these planets are huge. They're really big. They're like the size of like Jupiter or Neptune, and they're really far away. So that's one way to do it on Earth. We have this thing called an atmosphere that makes it really hard to do. But if we send things into space, it's a little bit easier because we don't have to deal with our atmosphere, and we can get clearer pictures. So we have some future space-based missions. I call them fancy missions because they're really exciting. So what we're trying to find is a picture of another planet. Perhaps it looks like Earth. So this image that you're seeing here is from the Voyager spacecraft that was launched in 1977, and it got out to, I think, the orbit of, I don't know, beyond Saturn, and turned its cameras back to Earth. And we have a little image of what Earth looks like from far, far away. So we are trying to find pictures like this. We're trying to find Earth-like planets from around stars that are far, far away. So we want to get to something like this because we call this the pale blue dot. We can see that Earth is a pale blue dot. And with our technology, if we saw this around another star, we could maybe detect that there's water there, signs of life. It's very exciting. And the way we're going to do that is we need much bigger telescopes. So over here on the left is the Hubble Space Telescope, and it is 2.4 meters across, which is a really big telescope that we've put into outer space, and it's taking amazing photos. The next telescope that we're launching is called the James Webb Space Telescope, or JWST, and it's about 6.5 meters in diameter. And it's hard to launch these things. It's very expensive. This mission has taken a lot of time to build and to get prepared to launch. And it hasn't launched yet. So we're hoping in the next few years it will do that. But with the kind of quarantine happening now, it might take a lot longer. So the next telescope that they're hoping to launch after James Webb is the LUVOIR telescope. And there's a few different kind of missions proposed about LUVOIR. There's a LUVOIR A, which is a little smaller, and a LUVOIR B, or I might have mixed them up, but there's two different sizes and they're both going to be really big. And this will be our best bet for actually imaging exoplanets around other stars. But even with these big fancy telescopes, it's going to be hard to see the exoplanets because starlight is so bright. So you need to do something, you need to do some fancy tricks to get rid of that light. So here's what LUVOIR might look like if it's launched in space. Going to be pretty cool. So I was mentioning those tricks. So one way that we're trying to really block out the light of the star is by using something called a star shade. I don't know if anyone can see my talking face, but I'm holding up a model of a star shade, and it's supposed to look like the image here on the right. So this does a really fantastic job of blocking out the light from stars. So this is what one of the studies that's happening now is do we pair one of those space-based telescopes with something like a star shade that will block out the light of the stars? And you're probably wondering, like, what's the deal? Why does it look like a flower? And it turns out these petal shapes do a really good job of blocking out the light of a star. Compared to just a circle, like you see on the left here, we use these circles, we call them coronagraphs, to block out the light of our star, so we can see the wispy corona of our sun and nearby comets getting really close to the sun. So this works okay for something pretty close and pretty large like our sun. But if we're talking about stars really far away, they're super duper small to our eyes, right? And you have to block out the light way more efficiently than something like just a circle. So there's a fancy physics equation, something called a hyper-Gaussian equation that I don't have the tools to explain, but just know it's some fancy physics that basically kind of acts like those noise-canceling headphones. Have you ever used one of those headphones? So basically it's canceling out itself. The sound coming in is canceling itself out with the technology of the headphones. So the Starshade is kind of doing what those noise canceling headphones are doing, but not to sound, but to light. And it's the petal shape that really helps to do that. So here's like a old mission concept from a mission that I used to work on. And the name has changed. Now we're calling it HabX. But you can see we're going to launch the Starshade into space. And these things can be like up to 50 meters, I think, across in diameter. And then behind it, we're going to fly the little space telescope in the shadow of the Starshade so that we can see the light from exoplanets. And hopefully this graph isn't too confusing, but here's our star. Here's the planet we want to see. We're going to fly that Starshade into space and fly our telescope in the shadow of it. And we want to see the light trickle in from that little exoplanet. And on the bottom here, this is what we're hoping to see, a little pale blue dot here. So this is the light of the star blocked out. Here's some kind of residual gunk in our solar system. And this is the light coming from the planet. So if we could see a pale blue dot around another star, that would make me so happy, and hopefully you all so happy. So this is just a model of what we would hope to see with some of these future missions. And if you're really excited about this, that's awesome. It's a great time to get involved in astronomy and start learning about this stuff, because when you grow up, you might be able to work on one of these missions and help investigate these pale blue dots that we hopefully will find, and help to figure out if there's life on them. Wouldn't that be so cool? And with that, I'm going to end here.
Well, thank you so much, Julia. That was really interesting, and we are so thankful that you are spending the time to teach us all about space.
No problem. It's been a lot of fun, and I hope you learned a little bit today.
Thanks. Bye, everyone.
Bye, and Bella says bye too.
Bye, Bella. Thanks for watching, everyone. We hope you learned something that sparked your interest about outer space, and we'll see you next time